So in the past we had parametric functions. For example, I'm pretty sure I did one like this a long time ago. So t is going to be the parameter, and then this is going to be a vector valued function, sine of t, cosine of t, and then t. So if you only had the sine and the cosine part, then that would just make a circle and it would go around and around on the piece of paper. By having the z value get bigger and bigger, then imagine it goes around, but then it goes up into the sky, and it's much like a coiled spring. So its graph would look something like this. Let's see, when t equals 0, that would be 0, and cosine of 0 is 1, and that would be 0. So the y value would be 1. So if I started at 0, it would then coil around and be getting bigger as it goes up. But this right here is just like a thin piece of wire or something like that. Being that color, it could be copper wire. So what if instead of being thin like that, you wanted it to be like a ribbon, so that it's like 1 inch across, something like that. So for that, we need two parameters. And the two parameters we'll use are u and v. So for example number 2, how about if r is a function of u and v, and then make it like that. Sine of u, go with cosine of v, and then let the z value just be u. So let's go ahead and take a look and see what the graph of that looks like. So this is a pretty simple example of a parametric function. You can see that if you look at it this way, that definitely looks like either sine or cosine. But now it's got some width to it, so it's not just a line, but it's like a ribbon. And if you look at the u and you move the u, then this is basically giving the vertical information that it should be going up and down in this curved way. And then the v is providing the lateral information so that it's got a width, and it's not just a line, but it's like a ribbon. There it is. And then for example number 3, let's say z is equal to 9 minus x squared minus y squared. So you may remember from the beginning of the semester that graph would look like a circular paraboloid. And because of this 9, it would be up here at 9, and since these are subtracting, it then makes it upside down. So then it would be a nice circular paraboloid that would go around like that. It's got some curvature here, sort of try to make it look like it's in 3 dimensions a little bit. So now change this to parametric. So what I could do is I could just replace the x with u, and I could replace the y with v. So instead of it being a surface function, then we make it a vector valued function. So then r as a function of u and v is going to be these vectors. So the x component is just going to get replaced with u. And the y component is just going to get replaced with v. So that's basically just telling us x equals this, y equals this. And then plug that in over here. So the z component will be 9 minus u squared minus v squared. Now when we graph this in parametric form, it should be the same shape, although there is a little more information. So let's take a look at the graph and then come back to this one. Hi, you like my haircut? So let's look at this paraboloid here. This is the original version, x squared plus y squared plus z equals 9. And notice that the highest point right here is when z equals 9. Otherwise, it looks like nice circular paraboloid. Now, let's look at the same shape as a parametric surface. So this yellow part, it's the same thing, but basically the way that the parameters work is if you hold one of them constant, so the U is the blue part. If I slide it, it's pretty cool. So it travels all along the shape, sits to it snug. But if I hold that blue one still, so if that one's constant, and then look at where the blue and the red meet, so basically the red one is outlining the blue one right now, if you just concentrate on where they intersect. And so those two can create the whole shape. And we can do more with them coming up. Well, what we're going to do now is take a look at tangent planes. So hopefully you remember the equation for a tangent plane goes something like this. A and then x minus x naught plus b multiplied with y minus y naught plus c multiplied with z minus z naught equals 0. And then the vector that's in front, ABC, is orthogonal to the plane. Orthogonal or perpendicular to the plane. So you need a vector that's perpendicular, and then you can use this equation to create the tangent plane. Well, if you have a function r and it's been parameterized with u and v, then you would have the x part, which is a function of u and v. You'd have the y part, which is a function of u and v. And you'd have the z part, which is a function of u and v. So if you take the derivative, then there's actually two derivatives to consider. There's the derivative with respect to u, and it equals whatever. Derivative, derivative, derivative. And then there's also the derivative with respect to v, derivative, derivative, derivative. And so then each one of these is a vector valued function where you went ahead and took the derivative, and the derivative. And so you have these two vectors. So if you have two vectors and you need a vector that's perpendicular, how do you find it? That's right, cross product. So RU cross product with RV is what we're going to use to find the equation of the tangent plane. Okay, then on to example number 4. So for example number 4, R is going to be, the first component is just u times v, and then we'll have u times sine of v, and v times cosine of u. And then find the equation of the tangent plane. When u is equal to 0 and v is equal to pi. So for one thing, we're going to need to know the derivatives. So we need the derivative with respect to u. So this will be held constant. The derivative of u with respect to u is a 1, so the first component is going to be v. Then take the derivative of this u, which is 1, times sine of v. And then the derivative of cosine is negative sine, so it'll be negative v sine of u. And then we should plug in the 0 and pi. So the derivative with respect to u with 0 and pi substituted in is going to be, so the v is the pi, so this is pi. This would be sine of pi. and sine of pi is 0. And then this one would be sine of 0, and sine of 0 is 0. Now take the derivative with respect to v. So this would be 1 times u. The derivative of sine is cosine, so the u will stay there, and then it's going to be cosine of v. And then over here, the derivative of v is 1, so it's going to be 1 times cosine of u. And then substitute the 0 and pi. So u is equal to 0, which means that's 0, and this would be 0 times something, so that's 0, and this would be cosine of 0, which is 1. And then we need the cross product. So then RU cross RV, we've got the I, J, and K, and then the pi 0, 0, 0, 0, 1. So what is that? So when you cover up the I, then that would be 0 minus 0. When you cover up the j, that diagonal would be pi minus 0. And then when you cover up the k, that would be 0 minus 0. So now we have the vector that we need. We just need the point. So the tangent plane at, and then what would the actual point be? So go back to the original function, and if you substitute 0, that's going to be 0, that's going to be 0, and then this is going to be cosine of 0, which is 1, and substitute the pi, so the point is 0, 0, pi. Oh, right here I meant to say tangent plane at 0, 0, pi is, and now just do the little formula. You know what, I think I can even fit it right here. So use the vector, and these are the a, b, and c that go in front. So it would be 0 times x minus 0, and then plus pi goes in front of y minus 0, and then plus 0 goes in front of z minus pi, and then it equals 0. So this would be 0, because that's 0 times it, so that's gone. This is also gone, which means all it leaves is pi times y equals 0. That means the answer is y equals 0 is the tangent plane. And then let's take a look at the graph and see if that makes sense. So let's take a look at this function. First of all, what is that? Well, actually the parameters can help us understand the picture a little bit better. If I move the U, the blue one, then you could see it traces the shape, and then you can start to see some of the edges. Like right there, it looks like it's going straight, and right here, it's definitely curved. You can see this back part. If I move the red one, that looks like a sine curve or cosine. And as it goes up, then it fills this top part. Okay, now to the actual point. So what if I set the u equal to 0 and the v equal to pi? So I'm going to have to use 3.1. Oh, it won't go exactly on pi, but this point right here is what we're talking about. So that would be 0, 0, pi. Okay, then what's happening there? So what does the tangent line look like? Well, if you look at it and try to keep your eye on this point where they meet, then what does the curve look like there? Well, right there, it looks like it is a straight plane. So don't get distracted by this part, because this part is actually below what we're looking at. So we're looking at this part right here, which is basically a flat plane. So the tangent line would be a flat plane. And also when you look at it this way, then you can see it's going along the x-axis and it's going up the z-axis, which means that you have to keep y equal to 0. So not y equals 2, not y equals 4. This green one right here is the y-axis. So it seems that y equals 0 is the tangent plane at that point right there. And now let's look at the idea of surface area. So we'll go back to this first example, which is this paraboloid. And then suppose that we're supposed to find the surface area for the positive part, or the z is positive. So this one starts at a height of 9, it goes down like this, it makes the nice circular paraboloid. And then find the surface area of that shape right there. So right now this is not in parametric form. So the way that we did it in the past is you take the derivative with respect to x, you take the derivative with respect to y, you square those, add 1 and put it in a square root. So the derivative with respect to x is going to be negative 2x. The derivative with respect to y will be negative 2y. And then the surface area is going to be a double integral. And then you square each one of these. So negative 2x gets squared, 2y gets squared, add a 1, and then either do dx dy or dy dx. So I'm not actually going to integrate this one, because what I'm trying to do is point out how we could do this in parametric. So anyway, this is going to be 4x squared plus 4y squared plus 1 dx dy. And if we were actually going to integrate this, then I would say let's change it to polar form, because that would probably be easier. But now do this with parameters. So as I did before, make it a vector valued function with parameters u and v. And so it's going to be replace the x with u, the y with v, and then this part's going to be 9 minus u squared minus v squared. So next, find out the derivative with respect to u. So that would be 1, 0, and negative 2u. Take the derivative with respect to v, which would be 0, 1, and negative 2v. And then just for fun, let's find the cross product. So RU cross product with RV. Here's the old I, J, and K. And then we'd have 1, 0, negative 2u. 0, 1, negative 2v. And then, what does that equal? So using the old pen trick, if you covered that up, this would be 0, and then subtract a negative 2u. So if you're subtracting a negative, it makes it a positive 2u. And then cover up the middle one. And remember, this component needs to be multiplied by a negative 1. So this would be negative 2v and then minus 0. So it'd be negative 2v, but then the middle one needs to be multiplied by a negative 1, so it becomes positive 2v. And then when you cover up the k, that is going to be 1 minus 0. All right, supposedly what I'm doing has something to do with this. Let's see. Next, find the length of this vector. So that would mean take the square root and then square each one of its components. So 2u gets squared, so that's 4u squared. 2v gets squared, so that's 4v squared. And then 1 gets squared, so that's 1. And then take a look at what we had previously. So what we had previously was inside the square root, 4x squared plus 4y squared plus 1. That's the old-fashioned way to do it. Then, if you look at that, it's the same thing, 4u squared plus 4v squared plus 1. So finally, summarize by saying for surface area, the area of the surface will equal the double integral of the length of RU cross product RV. And then you decide, should I do du first or dv? And then for example number 6. So example 6. C is equal to the square root of x squared plus y squared, which you may remember, that is a cone. And then find the surface area. Find the surface area of that cone for the part of it that lies between y equals x and y equals x squared. So first of all, make this into a parameterized function. So r equals. So replace the x with u, replace the y with v, and then replace the z with the square root of u squared plus v squared. And then we need the derivative with respect to u. So that would be 1, 0. And then take the derivative of this square root function, which will be 1 over 2 times the square root. And then because of the chain rule, take the derivative of the inside, which is going to be 2 times u. And then the 2 that would have been down there and the 2 that would be right there, they can cancel each other out. The derivative with respect to v, that would be 0, 1, and then it would look very similar to this, except it would have v on top and then the square root on the bottom. And then find the cross product, RU cross RV. I, j, and k, and then this row would be 1, 0, and u over the square root of u squared plus v squared, and 0, 1, v over the square root of u squared plus v squared. So this part, that diagonal would be 0, and then it's going to be minus this one. So the first entry is going to be minus u over the square root of u squared plus v squared. Then for this one, so keep in mind that the j component needs to be multiplied by a -1. So multiplying this way, the main diagonal would just be v over the square root, and then minus 0. Then this one needs to be multiplied by a negative, so it's going to be negative v over the square root of u squared plus v squared. And then finally cover up the k, and this would be 1 minus 0. Okay, now find the length of this vector right here. Luckily, I have a whole pile of paper sitting right here, so I could just keep going and going. It looks like it's going to be a mess, but it actually turns out to be pretty nice. So find the length of RU cross RV. So that means it's going to be the square root of, and then square each one of these. So this one would be u squared, and when you square the radical, it's gone, so it's just going to be u squared over u squared plus v squared. And then square this component, so that's going to be v squared over u squared plus v squared. And then square the 1. Well, when you add these, they already have a common denominator, and what's going to happen to the numerator is it's going to become u squared plus v squared over u squared plus v squared. So we've got u squared plus v squared over u squared plus v squared plus a 1. And then that is a 1, and 1 plus 1 equals 2, so after all of that, it simplifies to just be a square root of 2. So believe it or not, all we need to do is double integral of the square root of 2. Now, what's the area? So that is where this part comes in. And I've changed over to u and v, and I let's see, it was the u is equal to x. So this would be the u-axis, this would be the v-axis. And then this one is just a straight line, which is just like y equals x, or the line v equals u. And then this one is a parabola, so it's a parabola going like this. And that's the parabola that v equals u squared. So then we could say this is going to be the double integral of the square root of 2. And then I'm going to do dv and then du. And so the v needs to go from here to here. So it's going to go, v is going to go from u squared at the bottom to u at the top. And then where these two are equal, so where does x squared equal x? That would be the number 0 and the number 1. So it's going to go from 0 to 1. Wow, isn't this amazing? After all of these cross products and all this stuff, that's all we have to integrate. Okay, so that means it's going to be, the antiderivative will be radical 2 times v, and that gets evaluated from u squared to u. And last, we'll need to integrate from 0 to 1. So then this is going to be, well, I could just factor out the radical 2. And then it's going to be the top one first, so it's going to be u minus u squared. And then do the antiderivative, so this is u squared over 2 minus u cubed over 3. Don't forget the radical 2, and evaluate that from 0 to 1. So finally, this would be 1/2 minus 1/3, and then minus 0. 1/2 minus 1/3. So that would be 3 minus 2, so that's 1/6. So finally, it's radical 2 over 6. Ta-da!